I am very cognizant about the fact that our experience is probably the barrier towards innovation.
Welcome to Stories from the NNI. This series features voices from the U.S. National Nanotechnology Initiative. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. In this episode, I spoke with Dr. Philip Wong, a professor of electrical engineering at Stanford University. I caught up with Philip during the 2017 NSF Nanoscale Science and Engineering Grantees Conference. Thank you for taking the time to talk with us, Philip. Could you tell us a little bit about your work?
Thank you. I'm a professor of electrical engineering at Stanford University. My main research area is electronic devices. So we build tiny electronic devices that eventually may go into one of your electronic products that you may have either in your pocket, on your desktop, or on your lap.
I noticed that you are interested in making sure that your discoveries translate into usable products or technologies. Could you talk a little bit about an example of where that has occurred over the years?
That's right. I started my career at IBM Research Laboratory before I moved to Stanford University as a professor. So that experience really shaped my view of how academic research is being done. I believe in the field of engineering, things that we do, the research that we do has to be useful. So many of my research is aimed at translating discoveries, fundamental discoveries in nanoscale science and technology into useful technologies.
I noticed that you have a CHIC program, chip in cell, for autonomous biosensors. I was reading about the cell's uptake in RFID tag. Could you talk a little bit about how do these cells communicate with systems outside of the body?
It's very interesting that you picked up that particular topic. Most of my work is aimed at building electronic devices for the semiconductor industry. However, when I get to Stanford, I realize there's a big, wide world out there that have problems that needs to be solved. And those problems can be solved through various techniques that we have developed for the semiconductor industry, such as building computer chips. So this tiny chip and cell project is an example of that. When we build electronic devices, we can build very, very tiny structures. Some examples are RFIDs, radio frequency identification tags. Those RFIDs you can find in maybe retail stores in which they would tag the merchandise. They're basically just a piece of metal coil in a coil. So we take a very similar approach in designing these tiny RFID tags. We built a very tiny passive coil of metal, nanoscale, and put it on a chip. And these chips are supposed to go into living cells. And one could potentially also build sensors that react to the environment within the cell. Now, you may ask, why are we doing that? In one of the afternoon coffee breaks with my colleagues in the medical school, and one of them asked me, wow, you guys build very tiny things. What can you do for us? Can you find out something about what happens inside a cell? I said, well, you could do that if you can insert some sensors inside the cell. And so I started asking them, how big is the cell? He told me, well, the cell is huge. The cell is 20 microns, 30 microns big. I said, wow, this is huge. We built the entire circuit that are less than a micron. So how about I build you something that can go inside the cell? So that started the collaboration with my friend in the medical school and also with another faculty in the electrical engineering department. She is an expert in wireless communications. She applied the same knowledge to help us design the tiny coils. The coils are tiny because it has to be small to go inside the cell, and it's a difficult thing to do. It requires some really fundamental theoretical breakthrough to understand how you could make such a small antenna respond to radio frequency waves from far away. We have already been successful in inserting the tags inside the cell and watching how the cell reacts. The next step is to basically sense the presence of the tag inside the cell and also build a sensor that creates a sensor signal that the a tag would react to and then beam the information outside of the cell.
Well, thank you so much for that explanation. I think you answered all the questions I had leading up to that, with respect to collaborating with MDs or clinicians, which clearly you're doing. And I think that the application of nanotechnology along the intersections of disciplines is what really helps make it so exciting, at least in my opinion. The other reason I really brought that example out is because we have a signature initiative in the National Nanotechnology Initiative focused on sensors. And one of the issues is you can use nanotechnology to detect a nanoparticle or a small signal, but there's always this challenge of communicating, and the approach you're taking with the RFID tag, I think, is really wonderful. Could you talk a little bit about how you interact with students, and do you work with both undergraduate and graduate students?
Yes, I do work with both undergraduate and graduate students. I have a regularly scheduled class on that is at the freshman level, and the class introduces to the students what nanotechnology is. The name of the class is What is Nanotechnology? So it's a rhetorical question, and so we introduce to the students what this nanotechnology is about. And oftentimes I find undergraduate students who are interested in doing research and sweep them into our laboratory to work with our grad students. And the grad students, basically, they come in and they tell us what they want to do in their own research, and we provide them with the facilities and basic background and the knowledge to get started. And oftentimes, the way I interact with the grad students is they would drive the definition of the problems themselves and carry out the research themselves. And then you may ask, what does a professor do? Well, the role of the professor is more like a football coach. We provide guidance in the events that they are a little bit uncertain about which direction to go. And sometimes our experience will help in finding out new directions and also weeding out directions that probably may not work based on our own experience. But oftentimes, our experience are wrong. So I am very cognizant about the fact that our experience is probably the barrier towards innovation. So when a student said, I want to do this, and I think, well, probably it won't work, I wouldn't tell them not to work on it. I just tell them that, well, probability is low, but please go and try.
It sounds like a really fun environment to pursue research. You're researching a number of different areas, and I think they're all fascinating. Is there one in particular that really has you energized?
Well, the thing that we are working on very excited about and working on spending a lot of time on is working on energy efficient computing. Much discussion have been said about the lack of progress, impending lack of progress in computing performance and computing energy efficiency in hardware. My colleagues and I, and many a group of people from Berkeley, Stanford, and Carnegie Mellon, have done a very serious and rigorous analysis, and we decided that we have come to the conclusion that another 1,000 times of improvement in energy efficiency can be had if we can do the right things. And this can be done in conjunction with the two-dimensional scaling that we have been using to improve our electronics so far. The scaling of dimensions have more or less come to a very slow plateau, and the impression generally in the community and also in the broader society is because the scaling has come to a very slow end of a plateau, that there will be no more advances being made. But that is not true, because the way we have been obtaining performance increases and also energy efficiency, even though it has been due through two-dimensional scaling, it doesn't mean that future advances have to depend on this particular method. And what we believe in is the advances will come in building electronic circuits in the third dimension, building three-dimensional integrated circuits. That requires new materials, new fabrication processes, and also new design techniques, because devices now will be situated in 3 dimensions instead of 2 dimensions. And those kinds of techniques can lead you to better energy efficiency for conventional computing architectures, as well as new computing architecture based on understanding or emulating how the human brain does the computation.
The work that you just described is certainly in support of the National Nanotechnology Grand Challenge that was launched a short time ago in future computing. So it's exciting to hear of your progress in that area. Is there anything else you'd like to share with the listeners?
Certainly. Today, you hear a lot of excitement about AI or machine learning and so on. That advances will bring us sort of to the next level of human and computer interaction, and also computer aiding human. Now, a lot of times people think that all we need is computers and algorithms and software. But in fact, if you think about what physical things actually execute those algorithms, it is the underlying computing architecture and the computing hardware and the devices and the technology. And those expectations that we have for machine learning and artificial intelligence, such as self-driving cars and so on, would not be realized if there is not a corresponding advance in the computing hardware. And those demands to the hardware is extremely stringent. It requires at least 2 or 3 orders of magnitude improvements in over what we have today. So advances in computing hardware is absolutely essential. In other words, hardware for AI is absolutely essential.
And that hardware will depend on nanotechnology. Is that fair to say?
It is definitely fair to say. Even today, traditional silicon CMOS technology is already at the nanoscale. 10 nanometer silicon technology is already in production. 7 nanometer and 5 nanometer have already been defined in key industry leaders. And going forward, the companies do not see any barrier going towards 3 nanometer or even 1 nanometer. So advances will continue to be made across the world.
Well, thank you so much. I appreciate your time this afternoon and really enjoyed our conversation. Thank you.
Thank you for the opportunity to speak with you.
Thank you for listening to this episode of Stories from the NNI. If you would like to learn more about nanotechnology, please visit www.nano.gov and check back here for more stories.